treatment processes related to looking at disinfection byproducts, trying to look at both reducing DBP precursor concentrations as well as removing them after the formation. And with that, Lynn, I'm going to let you go ahead and introduce your team and presenters.
Great. Well, thanks. So I want to clarify this project just a little bit because, especially based on something Chris said earlier, is one of the things that we proposed in this project that we think is really critical is that as we develop new technologies or look at or consider novel technologies, that it is important to consider the mature processes or even evolving processes at the same time. And so we're not just looking at saying, let's look at a novel process. We want to look at it in the context of what other processes are out there. And so as we move through this project, that will be a key to our analysis. So the people who are working on this, Des Lawler is integral in a number of the projects, and I'll point them out. Frank Seibert has been key to the first project I'm going to talk about. Frank is a researcher in the what's called the Separations Research Program. He's an amazing guy. He has 30, 40 years of programs running full. We have, I guess, the largest contactor systems in a laboratory-based setting. So if you drive by on your way out or look, you'll see very tall distillation columns. Those are part of his unit, and he's done a lot both with extraction systems, distillation systems, and membrane systems. So he's been collaborating with us on this. Mitch Bartolo is going to be talking, Mitch is going to be talking about some of the extensions of the alum coagulation work to focus on the organics removal, trying to get at some of the mechanisms of that work, of that process. And then Nash is working on some of the hollow fiber membrane air stripping work, and so Yun is working on and is going to present looking at the work that we've been doing on combined electrodialysis, reverse osmosis, or nanofiltration systems. So as a brief introduction, as I said, the goal here is to look at emerging and novel technologies for removal of DBPs, precursors and DBPs. We're looking at doing a literature review, and we took a lot of flack for putting this literature review into our proposal. And I have to say it's the first time I've ever been criticized for wanting to look at the literature, but fair enough. But I want to make sure you understand why we wanted to look at the literature.
You didn't give me that much credit.
But the reason that we thought the literature review is important is because while many technologies were examined over the past several decades, they're typically examined for their potential in large-scale systems. And in some cases, when you look at a small-scale system, the criteria for evaluation and even the cost analysis changes. And we like to think of this as like reverse economies of scale, is that there are some systems, membrane systems in particular, that when you have a membrane system, it is often, because membrane systems you just buy multiple contactors and their replacement is the same, number of years, you can actually find that at a small scale system, they are more cost competitive with things like granular activated carbon or other things. And so we wanted to look at these technologies and examine them. The other reason we want to do the literature review, and as I'm going to show you, with some of the technologies, one of the things that happens is that the technologies evolve. And and as they evolve, the conclusions that are made on their potential aren't necessarily the same as they are today. So that is part of what we're doing as we look at these technologies. We're also looking both at emerging and novel technologies, but we want to compare those to existing or what we call mature technologies. Okay. What we're obviously targeting here are systems that are violating disinfection byproducts, and that can benefit from either precursor removals or DBPs themselves. And our focus on DBPs is on the trihalomethanes themselves for at least this work that I'm presenting with my colleagues. So most of the work we're going to look at is going to be development and concept innovation, but because we're going to be doing some discussion of the alum coagulation process, I included it also in the implementation as well, since we're doing pilot demonstrations of that. So when you go to look at DBPs or and their formation, you can act on a number of things. You can either act on the disinfectant itself, you can act on the natural organic matter and remove that, or you can remove the trihalomethanes. And all of these options have been explored. If we look at DBP removal itself, the mature technologies are GAC adsorption and packed tower aeration. The evolving technologies are nanofiltration, clear well stripping. I like that as the evolving technology. It's always good just to put a pipe down there. And hollow fiber membrane air stripping. And I'm not putting this as a novel technology because it's actually been around a long time. But I'm going to show you some of the innovations that actually happened in the 1990s, which sort of happened right after a lot of the work was done with it. So, in terms of removing disinfection byproduct precursors, alternative disinfectants clearly can be looked at. I put ferrate up there in green to promote our ferrate collaborators. I'm thinking of starting my own ferrate production company. I'm sure you guys have been thinking about it.
Oh, good.
Anyway, and then in terms of technologies, for precursor, ion exchange and GAC adsorption would be the mature technology. Certainly people have looked at membrane filtration, both nano, ultra, and RO, as potentially an evolving technology. And I'll say enhanced coagulation is somewhat evolving, although I would call it somewhat mature as well. But because we're giving it new potential and looking at it from a little bit different perspective here, I sort of left it in evolving. Though I'd be perfectly happy to move it to mature. And then our novel technology, which is electrodialysis and reverse osmosis, which I hope you'll be excited about, but we'll see. And so I'm going to be talking about the first of these, the hollow fiber membrane air stripping, because Frances Sullivan, who's a grad student who initially started working on this, graduated in December, so she is gone. And she did a lot of the modeling, preliminary modeling of this and cost analysis. And Nash Mock, who's back here, has just gotten going on building and getting the experimental system running. And so I'm going to spend a little bit of time talking about that. Okay. So the first thing I want to point out about this hollow fiber member air stripper is that these are being used for air stripping. People are using them for CO2. They're getting a lot of industrial use. You can buy them in lots of different sizes that fit lots of different flow rates. You can put them together in series. And I want to move this thing because I have something on the bottom of the slide. What?
The Amazon drone will be dropping.
Exactly.
Treatment plant soon.
Exactly. Couple of things I want to say about this system. Certainly, it undergoes the same gas transfer fundamentals as an air stripping system, although there's some key differences between an air stripper and a membrane system. One has to do with the mass transfer resistance across the membrane itself, but one of the key features that we're going to be looking at is that these things tend to work more like stage processes, so more like trays, whereas an air stripper is more like a contactor, or is a contactor. And that has some key differences in terms of the effects of area and flow rate on mass transfer area. So there's some advantages here that often don't get looked at in terms of the potential. Okay? But in general, we still look at a concept like a stripping factor, and we certainly are driven by Henry's law. Okay, so here is the hollow fiber membrane air stripper. These were the original version of this that was being sold before about 1989, 1990. It's what we call an unbaffled module, and if you look at it, you have flow in the air side coming across in the lumen, and then in the shell, the water's coming through, and the concept is it's supposed to go like that. But the problem was it actually goes kind of like that. And as a result, a lot of the original work that was done with these got reasonable removals, but they weren't as good as they could be. And so that led to a modification of this system. But even so, if you look at this, you'll see that people operated these in batch mode, got 80 to 90% removal of chloroform, toluene. Amy Zander, this work we looked at quite a bit. She was getting about 80% removal of chloroform, BDCM, and bromoform, and a lot of the original work was done with this. Now, the other thing you notice, 1989, this was done with the unbaffled module. And the nice part about their work is they both did continuous flow. Okay. So one of the things we did is we looked at predictions of the mass transfer coefficient, the overall mass transfer coefficient in these experiments. And what you see in all cases is that the prediction is overestimating the removal that was observed experimentally. We think this is because of the short circuiting. And so while you'd expect to get a lot more mass transfer, you didn't get it. So what happened was and in fact, Frank Seibert was actually part of did the experimental work that sort of verified that this system was basically short circuiting. And as a result, they ended up building this as a with a baffled system. And now you can see the flow is being radially forced, and you have something that looks a lot more like a staged system. So now you have stage 1 and stage 2, and you can now look at this as a very different type system than an air stripping tower. Okay? But unfortunately, most of the modeling or most of the predictions were based on models that treated this as an air stripper. And so that was the other problem that we saw. So there were a couple experimental systems that happened with the correct reactor. He had also worked with trichloroethylene. Unfortunately, they didn't run countercurrent. They sort of ran co-current. Kind of doesn't work so well. And this work's a little bit unique. Terafter's work, was a little more because they did vacuum assisted. But when we did the comparisons of these, in terms of the predictions of the overall mass transfer coefficients, what we found is then we're certainly getting much closer between predicted and experimental. And in this case, we're actually doing better than was predicted, but that's probably because of the vacuum assisted, the way it was run. But we at least think now we have a system that's actually operating like this staged, I want to keep saying contactor, but it's not a contactor. So went ahead and basically looked at trying to model the system with 3 resistances in series. And the big changes you need to make sure you have the mass transfer coefficient through the membrane. In an air stripping tower, you actually don't typically have to worry about these if you have very high Henry's constants, and so 1 over big KL is often equal to 1 over KL, where you're looking at the shell side mass transfer coefficient. And so we looked at each of these terms. We developed the model based on looking at the 3 different mass transfer coefficients and having relationships for them. Okay? And so we put all that into a large Excel spreadsheet, and that's how we modeled other people's data, and how we want to start modeling ours to see if we actually work this way. Now we use the Murphy efficiency equation, and this has actually been applied in liquid-liquid systems. So Frank actually had done a lot of work looking at using this model for the same membrane in a liquid-liquid exchange system. The concept here is that your efficiency is a function of alpha, and alpha is a function of the area, but that area doesn't change. So it's a constant. And this alpha term is basically related to how close you are to the vapor-liquid equilibrium. Okay, so the further you are from it, the farther below 1 that you are. Okay. And so you can predict an overall stage efficiency, and you can have a stripping factor, and from this you can start looking at efficiency. And in stage stripping, what happens is the efficiency is really what you're after. And so if you can predict the efficiencies, then you will be able to scale the system, because the scaling will be based on the efficiency and the area. Okay. So just to give you a little bit of idea what this looks like then, is we're looking at this as like a 2-stage system. The pore size in these modules is about 0.03 to 0.04 microns. We've verified that with SEM. There actually is distribution. And the spacing here is about 40 microns. The reason I tell you some of this is because now you have an idea, because one of the first things you think about membranes is fouling. So everybody's like, okay, so we haven't checked out the fouling for this for air water stripping, but here's what I do know. We have run this system, in fact, we have a patent on looking at oil-water separation with this contactor. And we have separated produced waters, frac waters, and in fact, the original work where we used this was a project looking at trying to extract oil from algae. And so we would take the algae, burst them open, right? So we break them open, and then once we break them open, we have all the algae parts. So now you have like algae mess, and you put it directly into this contactor, and this thing ran for months. And so while fouling can be a problem, we haven't seen it, at least on the liquid-liquid size, with these, because the spacing is large and the pores are pretty big. So, and it is in these pores where you're getting the mass transfer. So that's where your liquid film is to get that mass transfer. I will also say that when we did this with oil-water systems, we actually even ran it really, in these algae systems, very high salinity, brackish water. And we did okay. We did fine. In fact, we never saw it clog. I think that's not true. We saw it clog once, and that's when we actually, when we used chitosan to coagulate the algae, and we created these like mats. It didn't like that. But in any event, when we looked at looking at the stage efficiency modeling, looking at predicted versus measured for the 3 experimental systems that we looked at, we put Xander in there, even though it was really run as a 1-stage system, but and then the vacuum-assisted work, and then the work that was actually run concurrent. You can see that one could say, like all over the place. And these lines are plus and minus 20%. But what this told us is we still have work to do. So if we really want to look at applying this or even evaluating it, we need to do more research. So that's sort of where looking at the literature and trying to understand what's there and what has happened has been insightful to us. Now, I don't want to ignore the fact that the other part of that is before we move forward, we didn't want to move forward until we actually determined that there was some economic driver that would make any sense at any scale. Okay. So this is not a great economic analysis yet. It's preliminary because we don't really have certainly the data for our system. We went into the drinking water technology cost model. So we used the, can't remember the name of the actual thing, but you go in, it's WRE, but I can't remember what it stands for. I don't know if anybody does, but you could, it's the, Scott, do you remember what it's called? The cost model where you go in and you can actually,
Water
what?
treatment model?
Yeah, it's the water treatment, but I can't remember the acronym. But anyway, you go in and you can actually put in the size of your system and what technology you're looking at, and GAC is in there. So this table actually goes from very small to medium. I don't know if you call medium 1 MGD, but we decided that was medium because it's our breakpoint. And so we looked at 3 different flow rates. We looked both at changing disinfectants, and you can see that's cheap. Not necessarily that it doesn't cause issues in itself, but certainly changing disinfection is a good thing to be looking at. And then we compared to nanofiltration and granular activated carbon. And what you see is that we're in the ballpark. Okay. So for us, this said, okay, let's push forward. Right? So we don't think this is our final cost estimate, but at least it says to us that in the scales of the systems we're looking at, we'll move forward. And when we did our scaling, I'll say, you know, we because these come in different modules, the size of the module changes and the number of modules changes as we move up in the flow rate. Okay. All right. So we did the preliminary economic analysis, and then we said, okay, we're going to do some experimental work. And Nash is going to walk us through.
So the goals that I've had in my research are to continue Francis's work and to quantify the THM removal in an air stripping system using continuous flow. And this is actually an unbaffled membrane, but we want to scale up to baffled membranes, so that's what we'll be looking for eventually. We want to look at the removal efficiency as it relates to stripping factor and to the concentration of trihalomethanes within the system themselves. And once we have this data, we're going to use it to develop a model which we can compare to the models Francis has looked at, and also to be able to look at the economics of scale using these membranes to scale up to a larger, perhaps pilot testing. So this means that we have to determine whether the system should be modeled as a stage device or as a differential contactor. Now, this is my experimental setup. I have a water feed which is contained in a Tedlar bag so that as it's being drawn from, it doesn't create any headspace for the THMs to volatilize into. This is pumped into my micro module and controlled at I've been controlling at a flow rate of 5 milliliters per minute using a rotometer above. And I've been taking samples at 5, 15, and 25-minute intervals from the sampling port, and then one sample at the initial to compare to determine removal efficiencies. On the tube side, so the water's going through the shell side, on the tube side, I've got 0-grade air coming through, and I'm controlling that with, at the beginning and end of the experiments, I'm using a bubble calibrator to make sure that my flow rates are similar throughout the experiment, and that is being pumped through the micro module, which I have a sampling port on the outside to complete the mass balance with the air and make sure that there's no losses in the system. This is the Liquicell micro module. It is where the air stripping is actually occurring, and I've got a couple of these that I'll pass around. And it has liquid flow limits of 5 to 30 milliliters per minute. I've been working on the low end of this range at the 5 milliliters per minute. However, I will eventually look up to 10 mils per minute. It's got an approximate surface area of 100 centimeters squared, and when it's fully primed, which means that the cell is full and the pores are wetted, it contains 3.5 milliliters approximately. At normal operating temperatures of 5 to 25 degrees Celsius, it's able to operate up to 45 psi gas, which we're nowhere near with the system. So, my system runs continuous flow. I've been varying my THM doses in my experiments, and I'm looking at 50, 100, 150, and 200 microgram per liter doses. However, so far I've only done experiments at the 50 and 200 increment. My water flow rate I've been keeping constant, but my air flow rate has been varied based on the stripping factors that I'm assuming, and then back calculating to get my air flow rates, and then at the end of the experiment, once I've measured the before and after of the flow rate, I can determine what the actual stripping factor of the system is. So this is just a little bit about the trihalomethanes I'm looking at. As you can see, there's chloroform down bromoform, and these are each adding on a brominated group in replacement of a chlorinated group on the methane. And as it's doing so, the Henry's constant is decreasing, which we expect with a lower Henry's constant, we will have lesser removal efficiency. So this was experiments I did with just trichloromethane, and I was looking at comparing different concentrations at the same stripping factor and different stripping factors at the same concentration. However, some of my data didn't look very good, so I had to work with what I had. And what I see is that I need more to fill in the gaps in the in-between concentrations and the in-between stripping factors to see how these parameters actually affect removal efficiency. This is very preliminary data that was gathered recently, and I'm still working to gather more to quantify these. Yes?
So you're just running a continuous flow, and does it come to equilibrium over time? It looks like it's changing a little bit over time.
Yes. So at the 5-minute increment, we actually determined that it may not quite be at steady state yet. However, after that point, it looks like it had approximately reached a steady state value. And so from there, the reason why it was reaching a steady state later is because it has to form the liquid gas interface within the membrane. Okay. And so that takes time. And so that's why you see a little bit of decrease over the beginning. But then once it's reached steady state, it's approximately constant.
Just want to warn you before you get too far down with the economic analyses of this work. The liquid cell membranes, the support, there's a support and then there's a hydrophobic surface which actually does the separation. The support is made of polypropylene. After about a year, it falls apart. Okay. People have used these in water and the chlorine just eats them up. They don't last. Bob Rasko has done some work with these. I've asked Bob for a report on them. Until Liquicell, we've tried to talk with them. We love the idea, we'd love to use these. But until Liquicell moves away from using the polypropylene support and goes to PVDF, these are basically a non-starter. Okay. They're that troublesome. They cost so much to replace that, I mean, we were getting ready to put a whole bunch of these systems in. And
so we've been actually working with Liquicell on a number of issues. So as I said, Frank was the person who actually got them to change the design.
Okay, if you could get them to change to PVDF, that would be great, because that would solve a huge problem. I just asked Bob from United Water about some reports, if he has anything, because he looked at some fouling, and there had been some iron fouling in it, so get you that, and have so you can look into it, because he had put in several, both for deaeration, but also for some THM strength. I mean, we had tried to work with him to do that, and said to him, this has a big payoff within the water industry. They didn't care. So maybe having a closer tie and listening to someone from that, because and with the the pore size of the support shouldn't matter for the separation so much. Right. So I mean, you could go to probably, I don't know, I won't venture to say, but it's the hydrophobic surface that does the separation. Right. And the PVDF shouldn't matter. Right. But are they going to have to cast it differently? How they make it gets in.
Yeah.
There was a small company who tried to get in touch with, out of, I wanna say, Northern Kentucky or Cincinnati, that did have a PVDF hydrophobic membrane, fell off the face of the earth. I can't find it, but if you could find that, again, something to work with.
Yeah, no, it's a great comment, and as I said, you know, our goal, and that's how we work with them with other systems, is that when you can show them, you know, we can present them data that the technology is economically competitive and that there's a market, then they'll start, but.
I mean, we were.
I'm sure you did, and
We
so-
tried to work with them and they were uninterested, so, yeah.
Yeah.
I'm surprised, I was surprised by it frankly, because, you know, we said, you know, there are hundreds of these potentially around the country. but-
Well, I'm glad you're excited about it.
Yeah, I mean, I was,
And-
it's both ways, I mean, it really made me angry, but no, it's a great technology and very easy to put in, and you don't need to vacuum the system in a
Right.
lot of places. In some places it does help,
Yeah.
but yeah, there's right as of now, there's a fatal flaw.
Yeah, and as I said, you know, until you know, I'm sort of obviously less worried about that part, because we have to get to the part where we can actually show. In fact, LiquidCell donated these so they've been working with us, so these modules are donated.
Right, but they actually, when we had some in for a year and they fell apart, they basically gave us replacement ones, and.
Well, there you go.
They also told us not to tell other people about that. It's not a sustainable business model for them.
Well, you know, they just got bought out, right?
I don't know. I mean, they've been selling them their membrana.
Yeah. Yeah,
So, I mean, it was sketchy. It was difficult and surprising. So I haven't seen when something that should be, yeah.
A win-win.
Right, it should be a win-win. Big membrane company back in the late 90s, US Filter, had bought out the Australian membrane company. That fell apart because it was a polypropylene membrane. We know from experience, they don't hold up in municipal water systems.
So how do these membrane systems compare economically with the storage tank duration?
I don't think, I mean, having put in a storage tank aeration system, we put in a couple, cost $20,000 to put that in. We get 25% removal, give or take. There is some, you know, operating costs. These might be a little more expensive. They're going to be easier to run, lower maintenance.
They don't fall apart.
They don't fall
If they
apart.
don't fall
If
apart.
it might.
If they don't work.
Yeah, I mean, they're.
But you know,
Well,
they're gonna get pros and cons.
Yeah, I mean, they're gonna get good removal, and it's gonna be the key.
Yeah, you're gonna get better removal through these.
Yeah, but you might not need that much.
Right. Well, then you can. Yeah, you can go with a
But you
smaller.
get
But you're trying to get it removed out.
You can put these places where you want.
Yes.
Most of the tanks are where they are.
Right,
If you
and
got
the
a
tanks
tank-
with common entry, exit.
Yeah, if
I
you,
mean-
you've got a high, you know, localized high concentration around the tank.
Right.
Would this ever make sense, or would you always go to the tank aeration?
No, I think there are places for both.
No, I'm saying, but in that particular case, though, you've got a tank, a hot spot.
You know, hold water in a hotspot
Yeah.
tank, you're gonna treat that tank if it's
Right.
reasonable to do so, rather than running the water out of the tank
Right,
versus
right.
dripping membrane.
Right, I mean, through the tank, you might, yeah, through this, you might have to treat, you know, several hundred gallons once. It's hard to split off. So hydraulically, the tank, maybe you're treating, maybe you're pumping 10 or 15 GPM in a small system. So
If you live in
Yeah.
a sunshine state, you could put a solar beam on the top.
What'd you say? What'd you say?
If you live in a sunshine state, you could put a solar beam on the top of your tank if you're done.
What your other things go.
No, we should move on to
Maintenance dollars, but
next thing.
it can be that
Uh,
easy.
Overriding
There's almost that good luck.
an economic question I posed to you, but just from a fact point of view, going ahead with this, I think you gotta get or write down some of these, you know, what fraction of DBP control problems are THM driven, since this won't do anything for HAs. So I just Right, you know, I just want, what's, we need to know. 60, okay, 60%, good.
And it's pretty high, I mean,
So it's, we need to know that fraction, to be able to say that.
yeah, no, I think it's, I mean, we have the same issue, it's like, you don't go after the HAAs, what's, you know.
Well, thankfully, biology does something for us there, right? So-
Yeah, it's another technology that is high.
I'm throwing one little small point, but there's a lot with the Henry's coefficients and all that, that the brominated ones are going to be removed less than the chlorinated ones. Of course, we regulate on the total. There's extreme sensitivity right now with opposite water with the brominated ones. I think everyone's sort of aware of that, but they're so and I think the experience so far is that they're removing pretty much all the THL species, even though from the Henry's coefficients would suggest the chlorinated over the brominated, but I think there's reasonable
Henry's
removal.
doesn't hold up in tank
Yeah, which
duration
is
because it's not in equilibrium.
right. So
condition, really.
so despite the fact that right, but there is some. So this technology is showing that you've seen already with the micro ones, with the brominated ones are less removed than the chlorinated ones. I don't know if that will hold true when you go to stage and all that, but.
Yeah, I mean,
but
you have
there's
to
some
look at it.
sensitivity there that OW would like to think that when we're removing the DBPs, THMs, we're not just removing the chloroform and then allowing the brominated ones to sneak up closer to that 60 mark where we're still in a safety margin. It's
60% or 60
no,
micro?
60. Yes, yeah.
I mean,
it's like
But
yeah.
but if you're removing 60% as opposed to 25%, you're still gonna be getting potentially more brominated ones, right?
you might have a high percentage of brominated, but they're still being removed.
Yeah, as long as its percentages overall move down, but does that allow now the window for the brominated ones to creep up higher in actual magnitude and still stay well? I just talk about 60.
Yeah.
That's most of
It
them are
doesn't
operate.
work that way.
Well, no, it depends.
You remove DBPs that are already formed.
Well, it
they're
depends.
reformed.
But now if you can drop the coagulant dose and use less DBP precursors and save some money in coagulant, because now, wow, with aeration, now I've gone from 60 parts of total THMs to 40. Wow, if I remove my coagulant dose, I can go back
They're
up to
not
60.
smart enough to do that.
Well,
only
it depends
that,
if
but
they're
they
willing
don't
to, now if they're
really-
trying
Because
to
their
justify.
coagulant dose is mostly driving for turbidity removal.
Well, yeah, but I guess I'm just doing another process though, in order to change.
We're in reality.
So, we should probably let Mitch
Right.
talk. Starting to fall asleep up there.
He's a grad student, he has time.
Yeah. All right. So hi everyone, my name is Mitchell Bartolo. I'm a second year master's student in the Des and Lynn cohort. And we're going to be switching gears a little bit, but still staying in the realm of NOM removal based on its repercussions with DBP precursors. I'm going to be talking about my research on NOM removal during alum coagulation in sites using infrared spectroscopy. Fluoride, aluminum hydroxides, and NOM that we don't quite understand. So what my work is trying to do is sort of look at the mechanisms underlying these removal mechanisms. And so because it piggybacks off of some of the pilot work, I included that here, but I'm sort of in this realm, still trying to figure out what are the mechanisms at play here. So just as a refresher, the alum coagulation process, we use jar testing. So we have coagulant and ligand addition in the front end and a period of rapid mixing, followed by a period of slow mixing to keep the flocks suspended and subsequent settling. And so what my research goals are is the characterization of these aluminum precipitates. And more so, what are the mechanisms of removal at play here? And so there are two main mechanisms that we hypothesize is occurring. So we can have absorption of the ligands to the surface of these aluminum precipitates, and we can have co-precipitation and actual uptake into the solid matrix itself. In the past, we've looked at SEM, EDX, XRD, XPS as some of the methods to kind of suss out what's happening with this co-precipitation. And what my work focuses on is spectroscopy to figure out what's happening on the surface with this absorption. It's also important to note that this process is very much different from sort of defined batch absorption experiments that you see in the literature, mainly because the co-precipitation and the coagulation and everything is occurring simultaneously over the time period of a drinking water treatment plant, and thus there are many processes happening simultaneously with these amorphous solids that are not well characterized. So it's important to really understand what's happening here. So some of the past work we've done, this is what we see here is Coulter counter particle size distributions on the left and SEM images on the right. The top is aluminum precipitates alone, and the bottom is aluminum precipitates in the presence of fluoride. And what we can see here is that fluoride is disrupting the precipitation process. We see much smaller particle sizes in the presence of fluoride, both in the Coulter counter results and in these SEM images. Furthermore, if we look at X-ray photoelectron spectroscopy results, so what these numbers represent here are elemental composition. And what we see is if we move from just the alum case to alum with fluoride and even more fluoride, we see aluminum oxygen ratios are decreasing and fluoride ratios are increasing, suggesting that these fluorine ions are possibly replacing hydroxyl ions in the solid. Even more so if we compare that to SEM EDX data, which actually has a deeper penetration depth than XPS, we see an even larger value, suggesting that there is fluoride deep within the bulk precipitate. Fluoride is co-precipitating. And so the methods of my test. So my tests included 4 weeks of repeated jar tests from 0 to 3 weeks aging. I mentioned that sort of all of the action happens over a time span of a couple hours. But we wanted to look at age of these precipitates to determine what happens with these ligands over time. And by understanding what happens as these ligands zorb or desorb, we know how they are attached in the first place. Varied experimental conditions. We did with and without fluoride, with and without NOM surrogates. We used an aluminum sulfate, aluminum salt, and aluminum chloride to investigate the effects of sulfate as a ligand. We used sodium metasilicate as a source of silica, 2 different pHs, one sort of at the sweet spot of aluminum solubility and one just above that, and fixed ionic strength, alkalinity, and hardness. These were all carbonate buffered and open to the atmosphere for some time, so carbonate is present. And my analysis of this, I used in situ ATR FTIR, attenuated total reflectance Fourier transform infrared spectroscopy, quite a mouthful. So we did that for the solids, and then we also got removal data from the supernatant. And so that resulted in this nice matrix. You see different organic acids with and without silica, fluoride, etc. And so in situ ATR FTIR is sort of insightful because it allows us to see what's going on the solid with virtually no preparation of that solid sample. So we're seeing what's happening in situ in the system itself. We're not changing sort of that bulk solid aqueous solution interface. So we can really see what's happening as far as absorption mechanisms. So ATR FTIR can tell us how much is absorbed and the mechanism of absorption. And so with that mechanism, we might have outer or inner sphere complexes. And with that, we can kind of tell what sort of competition is occurring among these ligands. It matches pretty well with the pyromolytic acid data, which leads us to believe that pyromolytic acid is a good NOM surrogate for us in this case. Furthermore, we can say that pyromilitate is a good NOM surrogate. So if we look at, on the left, we have squares are the pyromolytic. Darker colors are without fluoride. The lighter gray is with fluoride. And we see that both in the with and without fluoride case, we get much higher pyromolytic acid removal over this range of alum doses. And this matches pretty well with some past results we've gotten with Lake Austin NOM removal, lingering at about 80%. So we're pretty confident in the use of pyromolytic acid as our NOM surrogate, and we'll explore that more. Also, just as a sort of a side note, but you might have noticed that we sort of go between UV 254 data and organic DOC removal data, and we see great agreement actually between these two data sources for organic removal in our systems. And so what I'm going to do now is sort of walk through the FTIR results sort of ligand by ligand so we can get an understanding of how these things are attaching, and then in the end we can be informed about what sorts of competition is going on here. So with pyromilitate, what we're looking for, so in FTIR, for those of you who don't know FTIR, you're looking for these sort of fingerprints of vibrations based on functional groups that are on these molecules. So for pyromilitate in solution, not adsorbed to a metal surface, we would expect an asymmetric new CO vibration around 1560, a series of these symmetric CO vibrations in the 1325 to 1412 range, another aromatic vibration around 1490, and then a lower vibration that is attributed to aromatic CH bending. So if we look at the FTIR results for our adsorbed pyromilitate case, we see something that matches pretty well with the fingerprint of the aqueous pyromilitate in solution. So we have that 1562 vibration, that series of 3 symmetric vibrations here, and that higher aromatic vibration. And so what that tells us is because our adsorbed pyromilitate case strongly resembles aqueous pyromilitate, we're not getting any sort of substantial inner sphere complexation where we would see different bands, but rather we're getting outer sphere complexation due to the likeness with the aqueous pyromilitate signature, approaching more of that bidentate as they move higher. So that was interesting that we are in fact outer sphere complexed for sulfate as well. What we didn't see in these results, while we did not see a migration of these lower peaks to higher peaks, likely due to the fact that sulfate adsorbs very strongly in this range, we do see a strong increase in SiO-Si peaks over time, indicating that we have inner sphere complex silicate and polymerization of silicate on the surface over time. This is further supported by sulfate to silicate intensity ratios. As I noted before, we can learn about the magnitude of these ligand absorptions by the intensity of these peaks. And we see that sulfate to silicate intensities are decreasing with time in each of these cases, suggesting that we are getting more silica absorbed over time. Again, pointing to that polymerization of silicate on the surface. This is further supported by our removals data, where we see an increase in silicate removal over time in each of these cases. Again, telling us that silicate is inner sphere complexing and polymerizing on the surface. Noted here, silicate and fluoride were both theorized to be inner sphere complex, and we see that in each of these cases, fluoride removal is decreased in the presence of silicate, and here silicate removal is decreased in the presence of fluoride. Even on the larger, if we look at the larger trends, we see that fluoride removal is decreasing with time, as silicate removal is increasing with time. So it's interesting, as we're informed with these mechanisms of absorption, to see how these sort of competitions play out and what kind of implications that has on NOM as a DBP precursor in the system. So ATR FTIR allows us to determine both the magnitude and mechanism of absorption. We know that sulfate and pyro are outer sphere, carbonate, silicate, and F are inner sphere. And this mechanism-based competition between ligands provides an understanding that the background water chemistry impacts this NOM removal, this DBP precursor removal. And we can take some questions now. If not, Cian can come up, talk about her work on ED.
So Sarah, your comment about things sitting in the sedimentation basin and releasing. So this would be a good example where you might see something like that, because if the solids are starting to polymerize silica on them, you may see the release of that fluoride in that case. So it's kind of a nice example of seeing this.
Great, thanks.
Hi, my name is Soyun Kum and I'm a PhD student in University of Texas in Austin. And I'm going to talk about the coupled ED and RO or NF treatment. And this is novel, the part of the project. And okay, a coupled ED and RO or NF system that utilize the electrodialysis to isolate the salts that increase the falling in RO or NF, and reverse osmosis or nanofiltration to remove the NOM. So hypothesis of my research is that treatment efficiency and the number of the treatment cycle of RO or NF can be improved by isolating salt temporarily prior to either RO or NF. So here's the schematic diagram of the ED, RO, NOM removal system. The feed goes to electrodialysis first, and then we can get the ED diluate with low salt concentration and relatively higher concentration of the NOM. And then we feed this water, the diluate of the ED, to reverse osmosis. Then we can get the RO permeate to low salt concentration and also low NOM concentration. Because the RO get rid of almost all salts and also NOM, we need to add a little bit more salt from the ED concentration. Then we can get the treated water with normal salt concentration and low NOM concentration. So I think you guys may be familiar to the electrodialysis, but I want an introduction to electrodialysis. So here is the cathode and anode in the electrodialysis stack, and then in the nature, the cation in the water go to the cathode and anion in the water move to the anode. So we used that nature. We installed the cation exchange membrane and anion exchange membrane between the cathode and anode. Then we feed the solution. Then in the solution, the cation can pass to the cation exchange membrane, but it cannot go through the anion exchange membrane, and anion vice versa. So in the substream of between the cell pair, we get the pretty clean salt concentration water, which is the diluate, and we have high salt concentration, which is the concentrate. And because we use the electricity in here, we can produce the hydroxide and proton at the anode and cathode, and we rinse this water using electrolyte, catalyte and anolyte. So here is the experimental setup, batch recycled system. So the middle of the schematic diagram, we have the electrodialysis stack, and we supply the power to the stack. And then we have a diluate system with the mass. We can check the quantity change by the time, which is the salt and water transported to the membrane. And we circulate the water, dilute water, and also we do the same thing for the concentrate. We circulate the water over the time. And basically at the beginning of the experiment, we have the same concentration of the salt in the dilute and concentrate, and as the time goes, the salt concentration in the dilute goes down, and then salt concentration in the concentrate increases. And we have an electro rinse system, which for the supply the catalyte and anolyte to the electrodialysis. And also we have a flow rate measurement sensor, and we can check the flow rate at each streams. And also we have a six pressure transducers at each stream, inlet and outlet. Then we can check the pressure at each part and then make the water flow rate balance at the electrodialysis. And also we can measure the pH, conductivity, and also temperature at each streams, and all the data we can record and monitor by custom lab program. And here is the whole system of the lab scale ED experiment. It's pretty complicated, and you can see the electrodialysis system here, and dilute, concentrate, rinse, and we supply the power. And also we monitored and recorded all the data using the computer. And the current status and future work, actually this one is the very beginning of the research. So current status, I just verified the treatment of salt water with NOM and without NOM by ED. So future works, there are several things. The first one, I'm going to change the condition of the electrodialysis system, such as voltage, superficial velocity, and pH, and I'm going to find the optimum condition of the electrodialysis operation to achieve a high water recovery of it NOM contained water in our membrane processes. And also I'm going to conduct an experiment using different ion exchange membrane to verify the salt ion removal characteristics in different ion exchange membranes. And then I'm doing the NOM removal experiment of the ED, and I will combine the system by applying the selected optimum ED condition. And here's the treatment of salt water with NOM and without NOM by ED. So I use two different types of the water. The first one is 250 milligram per liter sodium chloride with 0.01 mole sodium sulfate solution without NOM. The second one is the 250 milligram per liter sodium chloride and with the concentrated Lake Austin water with NOM, which is the exactly same thing that John reported before to you. And I targeted the DOC concentration 5 milligram per liter, and I added some sulfate buffer. And also the conductivity of each of them is 0.82 millisiemens per centimeter, and pH is about 7.4. And here's the composition of the concentrated Lake Austin water, which is the same like John. And I diluted 1 to 20, this one. And here's the experiment operation condition. So I used the membrane type CMV and AMV, which is the commercialized membrane ion exchange membrane. And the step voltage, I applied the 1 volt per cell pair, but I used the 4 cell pair. I actually supplied the total 4 volt at this step. So flow rate is I just choose the 0.4 liter per minute, which is the superficial velocity about 2.12 centimeter per second. And feed water is a synthetic water, and I targeted the removal ratio of the salt about 80%. Here's the result of the treatment of salt water without NOM. You can see that at the beginning of the experiment, I have same conductivity at both the dilute and concentrate, and as time goes, the salt conductivity at the dilute is decreased, and then concentrate part is increases. It takes about 105 minutes to achieve the 80% of the removal ratio. And here is the treatment of the salt water with NOM, which is with the concentrated Lake Austin water, and the conductivity is at the beginning is the same, and then it takes about 80 minutes to achieve the 8% removal. So comparison of the salt removal with and without NOM, it takes less time at the salt with the NOM. I think the ion in the water and in the concentrated Lake Austin water, maybe some ion did the active with the membrane, something happens, so I need to verify what happened in there. The one thing I want to verify was ED is really good for the precursor removal, because the impact on the NOM concentration is really minimal compared to the salt ion salt. You can see the final concentration of the DOC at dilute concentration is 4.7 is about 4.7, pretty similar, and the removal ratio checking by the UV is about 10% is pretty low compared to the salt removal. So here's my conclusions. Effective removal of salt was achieved, and the TOC removal was minimal. So our has been demonstrated to remove an NOM, so these very preliminary results are promising. And
So to finish this off, we, for some of the fluoride and small water systems, we had something in the newsletter for looking at the alum work. Mitch just presented his work on aluminum hydroxide at ACS last week, so he's getting very practiced and polished at this time. We're going to put him on a tour. We're getting ready, just trying to finish up his dissertation, or his thesis, which will be the a paper that gets submitted on the FTIR results. We're also hoping this summer to finish the economic modeling and the components to look at the validation of the hollow fiber membrane. We'll make sure we put in that it's not chlorine resistant.
Okay.
But no, it's a really great point, and I think it's a great opportunity for us to be able to maybe do something about it.
Yeah.
So
We
that
can,
would be awesome.
I thank you if you could.
And,
The whole center would be worthwhile.
Yeah, exactly. So, anyway, that's, I think the end of the presentation.
Guess you have discussion.
Oh, yeah,
Questions?
discussion. I
We
think
got time
you
here.
guys discussed like that one project for like half an hour.
I'm sure we got more discussion.
Until our train of thought was broken, come on.
Any questions? The FTIR results may seem kind of esoteric, but we think they're key. And we think they're key because if you really want to know what's going on in enhanced coagulation, you have to know what's happening with the other components of the water chemistry. And if you start getting, if you're only getting 40% removal of NOM in enhanced coagulation and it drops to 30%, that's pretty significant in terms of what you're going to see in terms of DBPs. And I think what's really cool to me is the difference between sulfate and chloride. And we really want to explore that more in some of the macroscopic systems now, to go back and say, wow, are we, is there a big advantage to using aluminum chlorides instead of aluminum sulfates, or for NOM removal in these systems?
And what are the implications with respect to corrosion?
Yeah, all of those things. But I mean, I think but we wouldn't have seen that so clearly had we not done the FTIR work and seen, how different the competition is. And the silicate polymerization, it was really nice to be able to see that, and then getting to the point where, how long are the solids sitting in the basin, and are you going to get changes that occur, release of substances that you thought you removed. And this will be important when we get to the trace metals as well, and look at that. So we're kind of excited about that. All right, what did you think of the ROED idea?
I was just going to ask, have you done anything to look at kind of economics, meaning will the improvement in RO performance pay for the ED unit? Have you kind of played around with that at all?
We haven't done that at all yet. I will say, this idea came from Des and I sitting, around going, well, how come no one does this? How come no one's tried this? Because, if you can get NOM removal at that level, disinfection byproducts become,
I mean, if you can, in essence, target the divalent there, you do even a better job on the ionic strength.
Right. Absolutely. Yeah, so there's a...
I mean, people have looked at it, but it's never really done. Not necessarily with ED, but with other processes, with ion exchange processes.
CDI exchange mixtures.
Yeah.
Like mixed process, right? As well as ion exchange membrane.
The ion exchange
Right.
membranes that I'm aware of are not very selective. We looked at that in a previous project to think about whether you could do ED softening, basically. And at least all the membranes we could find, it was the difference between the ability to capture the calcium and magnesium on one hand versus, say, sodium on the other is not good enough to think of it as a treatment process. But I just want to say that relative to the comment that Bruce made, is that the idea here is that you're using the ED to make an initial separation. Then you're actually using both streams again. But then the RO is only using the one stream, so that you're basically allowing the RO system to operate much longer without fouling.
Right, yeah, the fouling issue could be worth it in and of itself.
Yeah. I mean,
You know, especially biologically, if you got rid of all of that.
I mean, comment on the ED running up at 4 volts where you're actually getting hydrolysis of water. There's a lot of lost energy
Yeah.
there. I mean, typically you want to run.
I was thinking of your catalysis project. We got the hydrogen now right there, so we're gonna get your
Right.
nitrates too.
But, yeah, but, I mean, it
At a
is
cost.
wasted
Yeah, at a-
energy
at a-
there.
Yeah, but just, when you have a full-scale ED system, we were using 4 cell pairs, they use 100 cell pairs, and basically the amount of energy you lose at the electrodes becomes a negligible fraction. In this system, it's a pretty high fraction, but that's really irrelevant for total operation.
I mean, instead of straight ED, especially again for smaller systems, capacitive deionization is out there, which is similar in concept to ED,
Yep.
but you're saving a good chunk of the electricity.
Yeah, no, that's a great thought. Yeah. But we like the idea of, separating the NOM like that, and, it could save a lot of problems in a lot of parts of the planet. And whether it's economical, as you say, we haven't even come close to that yet.
Do you see evidence of electrolysis of water in this?
Des has seen it with
Yeah, I mean, really in all ED systems you get that to some degree. It's pretty much inevitable. But I really don't think it's a significant problem.
So, how about other solutes?
Well, I mean, in the electrode rinse, you have to be careful. You can't use chloride-based things that you can get chlorine.
With the ambient chloride, you don't have.
Yeah, it's low enough that it's not a problem.
And other reactive oxidant species.
I haven't really looked at it in detail, but I don't think so. I mean, it's all happening with the electrode, and you're basically supplying the electrode rinse water as separate from everything else. So you can pretty much avoid that in any system. It's a really small stream that can be recycled even in a full-scale system. So I don't think that's a big issue.
I mean, if you are getting some electrolysis, you could be actually creating some A or C in there, so you might increase some biofouling potential in the RO.
Yeah, I mean, in the system.
But that stream doesn't go in the RO.
Yeah, it doesn't go in, so it's not gonna be a problem.
Yeah, there really are 3 streams, okay? I mean, there's the electrode rinse stream, which is really separate, and it's a tiny fraction, and then there's the treatment stream, which gets separated to dilute and concentrate, and those are the things that go on.
How big is the electrode rinse? It's in percent?
Well, in this system, it's pretty high, but in a full-scale system, it's a tiny fraction.
A few percent?
Yeah. I mean, in full scale, even in a small system before.
Yeah. Going back to coagulation thing, mature technologies, I think you could, for NLM control,
Absolutely. When I was, as soon as I looked at it up there, I just divided it back up this morning, or divided it up this morning. I didn't have it divided, and I went, oh, I should divide these, and as soon as I saw it there, I was like, ah.
But
thanks for pointing out.
Well, I'm just curious about your use of enhanced coagulation. I hate the term. It's a regulatory thing that makes no sense. So, would you be open to calling it optimal coagulation?
I would love to call it optimal coagulation.
Because it's a really annoying.
So I have a question for you all. Okay, so run an iron coagulation system. What pH do you want to be?
Well, mid-5s is our pick for our study that we've done, but for iron coagulation. But it's a flavor of effectiveness, right?
But what do you see? What do you see? What do you?
if you're a small system, you want to coagulate it, if you can, at whatever pH the water is coming in the door at, with the,
Which is,
with whatever pH you get, adding whatever amount of alum you're gonna use. You
So
don't
with-
wanna fool with
right,
acid,
but with the,
is my point.
yeah.
Yes.
So, but what do you, so what do you typically see at iron? Your stuff at like 7?
Yeah, we're
7, 8.
mid-sevens, yeah.
Yeah, and so, one of the things that, we always go, oh, iron does so much better at non-removal, right? But, we wanna be down at
You gotta do
pH
it right.
4 or 5, right? I mean, we're seeing optimal at pH 4, and so
Nobody's gonna operate.
nobody's gonna operate, right, exactly. I mean,
Not
if you
even a
looked at
big
those
system is
numbers.
dumb enough to that. If you have an acid base farm on your hands.
Yeah, so-
It's gonna cost you a fortune in chemicals.
Yep, exactly. So that was one of the things that sort of hit us when we moved into the iron systems is how, we knew it would be low, because we've seen that in the literature.
You could almost say for the same pH that you're at now, you'll remove more NOM with iron than you will with aluminum.
Right.
And you have more potential if you're willing to drive it down, but most systems aren't willing to drive it down.
Yeah, we didn't see that in these systems. So, because at the higher pHs, we did better with alum than we did with the iron, right? In terms
We're
of
talking
NOM.
again.
In terms of NOM.
It's similar at higher pH, like 6 and 6.5.
Huh? Yeah.
It's a pretty similar remover for both ferrochloride and alum.
Yeah, but as you moved up a little bit, it was like less for the iron.
Yes.
Yeah, so 665 is still pretty low
Yeah.
for a system.
For our system,
Yeah.
but where we have in the past had changed from alum to ferric at around the same pH, we
You did
typically
better.
got.
Okay, it's good to know. I just,
Yeah.
no, that's important because
And it's a constant battle I have, saying you gotta lower the pH, and they say no, and that's the extent of the battle.
yeah.
And you're not there every day. so-
Exactly.
Exactly.
And
No.
it's the same battle if you come into a plant and say, you could do like 20% better if you just switched to ferric, and they look at you like they're crazy because no one wants to run ferric.
Yeah. No, I was curious
Treatment
about this.
chemical that handles it's a lot, it's a really much more hazardous.
Much more hazardous, and nobody wants to go there.
Yeah.
Yeah, no, we like alum.
Just one of the interesting things to use the term that John hates, part of the enhanced coagulation rules are this business about you don't have to go farther than, if you get to the point where what's the point of diminishing returns, it turns out that when you have fluoride in the water, you reach the point of diminishing return way early.
Yeah.
So fluoride actually, because it's preventing some of that removal, you actually don't end up coming close to meeting the DBP, the precursor regulations, because you reach the point of diminishing return. Fluoride is not a very common problem, but where it happens,
It's a problem. Where it happens, it really happens.
yeah, it impacts this issue considerably.
It's time.
We have a little more time for discussion, but I suspect this group has discussed out. More discussion?
Hey, thanks for the great feedback. This has been
I think the
awesome.
movement that's afoot to avoid the enhanced coagulation labels might be a mistake. And the reason I say so is because everyone uses it and knows generally what it means, and if you give it some other label or come up with some other concept, you're gonna go down some path that will just create confusion among.
No, the battle was lost a long time ago. It's just, whatever.
John just doesn't give up.
So what happened though, John, I talk to my people about optimizing coagulation all the time, without ever saying enhancing it.
It'd be simple to say,
Hopefully have more to
they
it.
could have simply said coagulation to maximize NOM removal. And-
Well, you need to go to work.
And you can say that. You could say
I
that.
was there.
Did you get that- did you get those
can only
notes?
drive to so far, and then
Right.
the little people are gonna fight with those.
Oh, yeah.
people.
You know, maximizing NOM removal and maximizing dissolved aluminum turns out to be one of the goals. Yeah, can I make one?
Sure.
Lynn,
Yeah.
and you guys doing, so, ligands are phenomenally important in metal hydroxide precipitation, what they look like. And one of